In this lesson, we shift gears completely and move from talking about the structures of organic molecules to the reactions that organic molecules undergo. And implicit in talking about reactions is the concept of mechanism. So first of all, what is a reaction? Well, a chemical reaction is simply some process by which reactants or starting materials are converted into products. So one substance changes into another substance. A mechanism is the sequence of individual steps leading from starting materials to products in which the flow of electrons is indicated using curved arrows. And I will discuss curved arrows in much more detail on the next slide. So as an example to introduce reactions and mechanisms, we're going to consider a reaction that is probably fairly familiar to you, and that is the proton transfer reaction, also known as the Bronsted-Lowry acid-base reaction. Okay, so we're starting with this reaction because it is a simple and familiar with reaction with which to introduce the concept of mechanism. And secondly, because it is an important fundamental reaction in organic chemistry. As we will see later on in the first semester course and then in the second semester course, many more complex organic reactions, ones that have multi-step mechanisms, have proton transfer as one or more of the steps of their mechanism. So a thorough understanding of how organic chemists think about proton transfer reactions is a prerequisite to understanding the more complex reactions that organic molecules undergo. Okay, so the overall reaction of a proton transfer is that you have a base. We'll call it B, generic base. Bases frequently, but don't always, have negative charges on them. But what bases have to have on them in the Bronsted-Lowry definition is a lone pair. Okay, the base reacts with an acid. We'll call it HA. What an acid has to have on it is an acidic hydrogen. This is an equilibrium process. The proton is transferred from A to B, so we are now left with BH, which is what we call the conjugate acid of your original base. And then we have A minus after having lost a proton, which is the conjugate base of your original acid. Okay, so remember that a Bronsted acid's definition is that it is a proton donor, meaning that it must have an acidic hydrogen. A Bronsted base's definition is that it's a proton acceptor, which means it must have a lone pair of electrons. So in general chemistry, acid-base reactions were thought of from the perspective of the proton. We say that the proton is being transferred, it jumps from the acid to the base. So two ways that organic chemists think about this reaction, and fundamentally how organic chemists think about any organic reaction, first of all, is from the perspective of bonds. Okay, so an HA bond is broken and an HB bond is formed. And then second of all, from the perspective of electrons. So when we think about it this way, the electrons on B go and grab a proton from HA, leaving the electrons that were formerly in the HA bond on A. This way of thinking about reactions from the perspective of electrons brings us into the concept of curved arrows. And I wrote in red here that this slide is possibly the most important slide in the entire course. Any problem that involves writing a mechanism of a reaction, of which there will be many from this point onwards, involves showing how the electrons move during that reaction using curved arrows. Now, curved arrows are a different beast from reaction arrows. They're a different beast from equilibrium arrows. They're a different beast from resonance arrows. Curved arrows show where the electrons go during a reaction. So specifically, they show where electrons are going when a bond is broken. So if you break a bond, where do those electrons end up? And where they are coming from when a bond is formed. So adding curved arrows to the proton transfer reaction scheme that was up on the last slide, you can see that there are two arrows indicated in red. One starting at B and going and forming the BH bond, and then the second breaking the HA bond and putting those electrons onto A. So looking at this scheme introduces the rules that you must remember concerning the use of curved arrows. Number one, the tail of the arrow is at the source of the electrons, and the head of the arrow is at their destination. Rule 2, you need an arrow for each bond you break and an arrow for each bond you make. Okay, those are the rules. Now there are some corollaries or practical applications, if you prefer, of those rules. One is that the tail of an arrow will never be at a hydrogen atom. Okay, students frequently make the mistake, if they're drawing a mechanism, of starting an arrow at a hydrogen. But if a hydrogen atom is being transferred as a proton, it's taking no electrons with it. So no arrow can start at it. It cannot be the source of the electrons. The tail of the arrow, the source of the electrons, is always either a bond or a lone pair. Secondly, the head of the arrow will never be at a lone pair. It will only be at a bond if you're implying that this mechanistic step is forming a double bond, which does happen. The head of the arrow is usually at an atom. And then thirdly, in a correct mechanism for a reaction that requires two arrows, like the proton transfer reaction indicated here, the arrows usually follow each other head to tail. Okay, so can you see that? The arrow between the HA bond going to A has another arrow behind it whose head is close to the tail of the first arrow. If you draw a mechanism where two arrows are crossing each other or pointing to the same place, you're either making a very convoluted drawing or your mechanism is not correct. I want us to look at a real example now of a Bronsted acid-base reaction, of an organic acid-base reaction, rather than just using A's and B's. And we will show how you put curved arrows onto this reaction to indicate the mechanism. And that reaction will be the deprotonation of a carboxylic acid. So carboxylic acids are acidic functional groups. It's the hydrogen bound to oxygen that's the acidic hydrogen. As we move forward in this unit, we will see why that hydrogen is acidic, but for now, let's just take it on face value that that hydrogen is acidic, and when it is reacted with a strong enough base, it can be transferred to the base. So we will start with acetic acid as our acid, and NH3, ammonia, as our base. And take my word for now that NH3 is a strong enough base to remove the hydrogen from acetic acid. Again, later in this unit, we will do careful quantitative measurements to demonstrate that fact. So the reaction at the end is that acetic acid is now becomes an anion. It becomes the acetate anion, and the electrons from the OH bond end up on the oxygen, and that oxygen ends up with a minus charge. And then NH3 picks up another proton to make NH4+. Okay, so you make ammonium acetate. If we want to add arrows to this, we do the following. One arrow goes from the lone pair on NH3 to the hydrogen, and then the other arrow goes from the OH bond onto the oxygen, because those electrons are going onto the oxygen. Now, you may have noticed that I have put charges on atoms in the products of this reaction. We have not done very much at all in this course with charges on atoms yet. So in the next lesson, we will review, if necessary, or develop, if you're not familiar with them, the rules for when you need formal charges on atoms and what charge is appropriate to put on atoms.